Hello everyone, you are welcome to session 2 of this optimization theory part. In this part, or in this session, I am going first to start with an example, then we will extend it to to talk about concentrate and unconcentrate optimization, as well as this the steep descent optimization algorithm. So now assume that we have the cost function c of x equal to x1 square plus x2 square minus 5 x1 x2 plus 5 x1 minus maybe 3 x2 plus okay 5, for example. So just we assume that this is a cost function with two parameters. Here I want just to show you how to make the calculations, how to find the optimum point in this or the critical point in this cost function, and then how to check if it is like minimum or maximum or saddle point. This is what I'm going to explain in this example, how to do it by hand. As we showed in the previous section, first we start with computing the gradient of c of x, which is simply is vector with the partial differentiation of c of x with respect with x1 and c of x with respect to x2. Okay, so I will perform everyone separately. So with respect with x1, so we have dc over dx1 equal to 2. Of course, this should be 0. This will be 2x1, okay, 2x1 minus 5x2. This will be 5 plus 5, okay, and this will be 0 and 0, so this will be should be 0. And then this means that 2x1 minus 5x2 equal to minus 5. This is equation number 1. And then we take the differentiation with respect to x2. So this will be the same as with respect to x2, it is 2x2 minus 5x1, okay, and minus 3 equal to 0. And this means that we can just rearrange it to be the same as above. So it becomes like minus 5x1 plus 2x2 equal to 3. Okay, now we have nice like two equations into two unknowns, which can be solved easily with either by finding the inverse of the matrix or by just substitution. So simply in this way that we can put it as like 2 minus 5 minus 5 2, okay, times x1 x2. This should be minus 5 and 3. Okay, so it is clear that this matrix A, for example, is non-singular matrix, which means that it has inverse, because non-singular, because the determinant is not 0. 2 times 2 is 4. 4 minus 5 times 5 is 25, so it is not 0, which means that it is non-singular matrix. Then it should have inverse. Okay, uh, by making the inverse, so by using this my calculator. Of course you can do it easily also with hand, because you can make substitution. For example, you can say here that x2 equal to 3 plus 5x1 divided by 2, and substitute this equation into equation 1. Substitute this is equation 2 in equation 1, then you can find the value of x2, and then you can substitute back to find x1. So it takes like 1 minute of calculation, but using my calculator I can find that if my entry is correct, so x1 and x2 equal to minus 0.24 and 0.90 as an approximation. Okay, now this is the I can put here star, which means that those are the critical point of this cost function. Those are the critical point of this cost function. It means that it should be either maximum point or minimum point or a saddle point. Okay, how could you know what this critical point represents? Simply we can do that by computing the Hessian matrix. So the Hessian matrix is easily computed if you remember from the previous session, that we take the differentiation 2 times. Now this is dc over dx, and now we differentiate this once more with respect with x1, which means that if you make the differentiation with respect to x1, the result will be 2. And then the same equation, you differentiate it with respect to x2, and if you differentiate this with respect to x2, it will be -5. And then in the second row, we look to the differentiation of c with respect to x2, and we differentiate it once more with x1, so it gives also -5. And now we differentiate this with respect to with x2, it gives us 2. Okay, so this is the Hessian matrix. Is this matrix like positive definite or not? Is it, I mean, is the eigenvalues of this equation or this matrix is positive, strictly positive? It means that these points will be like minimum in this surface. If it is negative, then it is maximum. If it is mixed between positive and negative, or there is zeros, then it will be like an inflection point. Okay, we can easily find that by using the what is the eigenvalues. The eigenvalues is that one which makes the determinant of lambda I minus h equal to 0. Okay, which means that the determinant of lambda minus 2, it becomes 5, this becomes 5, and this is lambda minus 2. This should be 0, and this means that lambda minus 2 square, okay, minus 25 equal to 0. And this we can expand this one, it becomes lambda squared minus 4 lambda plus 4 minus 25. Simply it becomes lambda square minus 4 lambda, okay, and plus 4 minus 25, it becomes minus 21 equal to 0. And solving this, we got lambda equal to minus 4 becomes 4 plus minus square root of 4 squared is 16, minus minus becomes plus 20, 4 times 21 is 80, 84 plus 84 divided by 2. And okay, now we have lambda 1 equal to 7, and lambda 2 equal to minus 3. Why? Of course, because square root of 16 plus 84 is 100. Square root of 100 is equal to 10. So it becomes 4 plus 10 is 14 divided by 2 is 7, or 4 minus 10, which minus 6 divided by 2 is minus 3. So now we have lambda 1 and lambda 2, which they are like not the same sign. So it means that this point is an inflection point. It is not minimum and it is not maximum. Okay, so it is an inflection point. Okay, let us what you think that if we draw this function together with octave. Let me just switch on the octave, run the octave, and then we come back to make this calculations, or to see how will be the surface of this function. Okay, so now we can see this is the function here that we have. Okay, and first, how to draw the surface of the shape of this equation. In the beginning, let us define what is x1 and x2. Sorry, so it is x1 and x2 equal to, we can to draw it as a mesh, so we need to have to define the mesh grid, okay, of in the beginning, we need to define the values that we want the surface will be. So for x1, because the solution of x1 is minus 0.24, so it is good that to have something included this one. So let us start from -1 and with the step of 0.1 till 1. Okay, so this is good. And for x2, because that critical point is at 0.9, so we might also start, for example, from -1 for example, to, let's say, with a step point 1, and also we can go up to 2, for example. Okay, so this is the mesh of grid that we use. Okay, and also for the now we define the function y, or the function, the cost function actually, c equal to, as it is in the example, it was x1 square, so it is x1. We need to have the dot squared, because here x1 actually is a matrix, because it is a mesh, so it is a matrix. So we do it like dot square, and then plus, it was plus x2 square, x2 dot square. Okay, and minus 5x1 x2 minus 5 times x1 dot product x2. Okay, okay, let me see the function. Plus 5x1 plus 5 times x1. Okay, minus 3 times x2 minus 3 times x2. Okay, and uh, plus 5 plus 5. Now this is the function of the cost function c. Okay, now we want to see how it will be, so we put it like surface of x1 and x2 and c. Okay, so yes, this is the output. It came to my second screen, so I put it to this screen. So this is the cost function, how it will be the surface. Actually, I can also rotate it somehow. Yes, so you can see that this is the cost function. So you can see actually this point between, because you can see this is one is x1 and x2, and if you look to this point is a saddle point or an inflection point. It goes like up here, but it goes down in the other side, which means that it is saddle point. You cannot say that it is minimum or maximum. Okay, so yeah, so that is all about this simple optimization. Now we know how to make, what are the conditions to find the optimization. Remember here that we talk about unconstrained optimization, so we don't have constraints. We are just looking for what is the critical point, and then to check that critical point if it is maximum or minimum, or an inflection or saddle point. Okay, and now we understand how to do that. Of course, with hand you can do it up to three parameters, or three variables, x1 x2 x3. You can easily do it with hand. For much more like parameters, it is very like time consuming to solve them with hand. So there are some very sophisticated packages on Octave or MATLAB or Python that they can solve and find the optimum point for any cost function. Of course, remember always that most of these packages, they solve them by using iterative methods, because not easy. What I presented here is a convex simple function that can be solved by hand, so we can find the final solution easily. However, if we have like millions or billions of local minima or local maxima or many saddle points, then we use some iterative method, and those iterative methods usually they can stuck in any local minima. Of course, there are some algorithms to get out or to overshoot the local minima and find, or try to allocate another better critical point. However, that those methods based all of those methods based on the like what is known as steep descent algorithms, as well as some searching techniques, can be like random searching, or it can be systematic searching. We are not going to explain every optimization methods in this introductory part, but we will show what we need in this deep learning course. Okay, now we can just go to back to see what is the constraint optimization. Let me now remove this figure, and we go back to the uh, to the our whiteboard. Yes. Now we talk about the constraint optimization. Assume that it is the same actually previous cost function that we want that we wanted to minimize, as you can see that here, but now it is not a free optimization. We need to find the optimal solution according to some constraint. It is shown here, subject to. This st means subject to that x1 and x2 belongs to certain space. So we have certain set or certain space where below x1 and x2 is belongs to. Okay, so we are not looking for any point. We are looking only for the points which are belongs to this S. If you remember, assume that for example, assume x1 represents, for example, energy. Okay, and energy cannot be negative, so we need to have positive energy. Okay, greater than or equal to zero, for example. Or maybe x1 represents, for example, the price of certain gadget. So in that case, x1 must be also greater than or equal to zero. It is not possible to have negative price. Negative price means that you sell something and you give also money with that. Of course, in general, this is not this is not true in general. Okay, so now we need to have like what is the optimum solution according to some constraints. We have some constraints. These constraints, which is representing as, for example, certain space. For example, if this is x1 and x2, we might have certain space where it is acceptable solution here. So we have acceptable solution if the solution is inside that space. Outside this space is not acceptable solution. Even that solution was like a critical point, but it is not acceptable. For example, if this point is here, it is not acceptable. Okay, this is called constraint optimization. Okay, and in that case, this space usually can be represented as a set of equations. For example, we can have this constraint. I am looking for the solution x1 and x2, which makes 7x1 minus 2x2 equal to 3. For example, just example. Now this is constraint. This is called equality constraint. This constraint is called equality constraint. Okay, and I can have also some kind of inequality constraint. For example, x1 greater than or equal to 0, x2 greater than or equal to 0. Those are inequality constraints. Okay, I can put another constraint. For example, x1 minus x2 should be greater than or equal to 3, for example, or x1 minus 3x2 should be less than or equal to 1. So you can actually have any set of equations. So those equations usually like specify what is the set that we are looking for the solution in. Okay, so this is called this one is called like equality constraints, and this called inequality constraints. Okay, so now we have inequality constraints and equality constraints, and now how to solve this equation in the presence of these equality or inequality constraints. This actually given in examples which will be uploaded as well. So we will solve some specific problems, and we show in details how to find the solution in case of equality constraint or inequality constraint. But now we just talk a little bit about the theory of that. Okay, so let us talk a little bit about the theory of the quality or inequality constraint. Let us assume simple optimization problem just to explain it. Okay, and let us put this. Okay, now this is our critical point. It is here. It is x star. Okay, and now assume that this function, this cost function, is c of x, and we have some constraint, and let us assume inequality constraints. It is more tricky to talk about the inequality constraint. So we have inequality constraint that x should be less than or equal to, let's say, some value, maybe we call it like alpha. Okay, now one method to solve inequality or quality concentrate in general for concentrate optimization is to convert them from concentrate optimization to unconcentrate optimization by adding all concentrates, either quality or inequality, into one form. What I mean, just to make it general, try that we want to minimize C of x subject to, let us have that maybe two quality constraints that let us call them for the quality constraint maybe j of x equal to 0. Okay, this is one j1, j2 of x equal to 0. Those are called quality constraints. For the inequality constraints, let us call them any other function. Maybe I will say that f. So we have f1 of x less than or equal to 0, and f2 of x is also less than or equal to 0. Maybe f3 of x is less than or equal to 0. So now we have this general um, uh, 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 like and constraint optimization. Okay, now this we can convert them to we use Lagrange multipliers. We can convert this into unconstrained optimization. How to do that? We can define a new function now. Maybe we call it maybe e of x, for example. This will be c of x, okay, plus lambda or mu1 times j1 of x plus mu2 times j2 of x, okay, plus lambda 1 times f1 of x. I will explain what is the meaning of everything here, plus lambda 2 f2 of x times f2 of x plus lambda 3 times f3 of x. Okay, now we have only unconcentrate optimization, and now we apply exactly the same as we did before for the unconcentrated optimization. So the gradient of E with respect with x equal to 0, the gradient of E with respect with the multipliers mu1 and 2 equal to 0, and the gradient with respect to lambda of E is equal to 0. So we differentiate this equation with respect with x, and we of course here we have x vector. This is the reason that we bought gradient, not differentiation, because we might have x1, x2, x3, whatever. So we take the gradient of E with respect with x equal to 0, and also we differentiate with respect with every mu1 is equal to 0 with respect with mu2 is equal to 0, and also we take the gradient with respect with lambda and lambda 1, lambda 2, and lambda 3, and we put them equal to 0. Okay, now those mu1 and mu2 and lambda 1, lambda 2, and lambda 3, all of them those called Lagrange multipliers. Those called Lagrange multipliers. Mu1 and mu2 are the Lagrange multipliers for equality constraints. Lambda 1, lambda 2, lambda 3 are the Lagrange multipliers of the inequality constraints. Okay, now, for example, when you differentiate this equation with respect with the mu2, for example, or with the mu1, what you will get, mu1 is only here. So you will get another equation that you need to satisfy, which means that j1 of x equal to 0. Okay, and this equation, once it is achieved, what it means that this will be 0. So the added value here will be 0. Okay, the added value here also will be 0. And when you take the differentiation with respect with lambda 1, what you will get f1 of x equal to 0. Okay, and in that case, either you achieve this equation, which means that the added value here equal to 0, or lambda 1 equal to 0. So you have here, remember, lambda 1, the optimum lambda 1 times f1 of the optimum x is always equal to 0, because one of them must be 0. Either you achieve f1 of x equal to 0, or if not, then you should put lambda 1 equal to 0, and then in that case you have either this one or this one, which means that the contribution of this value will be also 0. So actually, when you solve these equations, it is the result will be exactly as minimizing this CO of x, but in the same time achieving all these points together. Okay, maybe for the quality constraint, it is clear that the contribution is 0. because regardless of the value of mu1 and mu2, positive or negative or whatever, since j1 and j2 equal to 0 at the optimum point, then this makes those contributions equal to 0, so there is no problem about this. But the point which might not be that clear, how this inequality contribute 0 to this equation, one at the optimum solution. Why? Okay. Actually, in that case, for example, to explain this point clearly, why the optimum lambda times the optimum f, for example, this is lambda I, this is fi, for any ith inequality, the optimum, the multiplication is 0. Why this happen? Let us take this simple example that I started with. Okay, now assume that I am looking for the optimum, this is x, this is c of x. What is the optimum x, which makes, assume that x star equal to 1, okay? This is the optimum point. Now I asked you question, find, minimize c of x, which makes x, and x must be less than or equal to 2, okay? Where is 2 now? 2 is here. So this is 2. Okay. We need x to be less than or equal to 2. Okay. In this case, this constraint is called like not active or inactive constraint. Why? Because if we stuck with this, if we achieve this one, if we put f1 equal to x, I mean f1x, this one, f1x here, x minus 2 less than or equal to 0, if we achieve this as an active constraint, what happened? I will lose actually, because I will stuck with a point where we can do better. Actually, we can do better than this point, because we can get even better result by going back. And actually, I didn't violate the constraint, because the constraint is less than or equal to 2. Then it is better to ignore this constraint and go back until x star equal to 1. Okay, is it clear? It is better, the optimum solution, the optimum lambda here is equal to 0. We should ignore this constraint. So lambda 1 here must be 0, because if we keep this as an active constraint, what will happen? The solution will be at x equal to 2, and in that case, the solution is not optimum anymore. So we can do better by ignoring this constraint. This inequality constraint should be ignored. How to ignore it? By putting lambda equal to 0. So in this case, lambda equal to 0 is the solution for inactive constraint. If the constraint is inactive, we should put lambda equal to 0. Okay? Yes. Now let us change it a little bit. So now it is not less than or equal to 1, but let us change here. So it becomes now greater than or equal to 2. This is our constraint. So this becomes our constraint now. This f, it becomes greater than or equal to 0, not less than or equal to 0. Now we need x to be greater than or equal to 2. Okay, now this constraint actually is active. This constraint is active. Assume that you would like to minimize you are looking for a price, the optimum price that minimize your losses in your business. Okay, but you have a condition here that, for example, the item that you need to sell must be, this is a condition, must be greater than or equal to 2. So this is like a strict condition. Any solution than less than 2 is not acceptable at all. Okay, now you have this constraint. Now this constraint actually becomes active constraint, because the optimum point without this constraint is less than 2, but it is like vital, or it is like necessary condition that x must be greater than 2. How to solve this constraint? You have no other choice. You have to take this constraint. You have to achieve this constraint. So the optimum solution here now is x equal to 2. Once you take x equal to 2, what it means? It means that f1 of x, which is x minus 2 equal to 0, becomes active because x equal to 2. It becomes active. So again, now this f1 of x, now it becomes the f of x optimum is equal to 0. Even lambda now is not 0. Lambda here, it can be greater than 0. Lambda can be 5, can be 10. So we can actually compute what is the optimum lambda in this case. However, the multiplication of lambda times f is equal to 0, which means that the contribution of this at the optimum point is equal to 0, which means that minimizing e of x is the same as minimizing c of x. But the difference that we take all these constraints into account. So this is the difference between the inactive constraint or active constraint. Active constraint, it means that lambda will be greater than 0, but the function itself it will be achieved at the critical point. Okay, or if it is inactive constraint, we found that lambda is less than or equal to 0, then it means that we can remove or we can ignore that constraint and we put lambda equal to 0. Okay, actually, I have a separate video to solve for the constraint optimization and also for with the quality constraint and also with inequality constraint. Both of them you can find them after this video. So you can find both techniques. But this is important to remember or to understand the difference between like unconcentrated optimization, equality concentration optimization, or quality constraint optimization, and inequality constraint optimization, and those like summarize the main concept. Of course, there are a lot of methods that you can apply, a lot of techniques that they might be more efficient than the others for certain kind of problems. So those are other details. There are many good books in the convex optimization or in optimization in general. Okay, there are different techniques to how to get out from local minima to search for better like critical point and so on. Thank you now for this session. Actually, I wanted in this session to give both the concentrate and unconcentrate optimization as steep descent, but it seems now the time is already done. So let us go to another video and explain the steep descent algorithm as one of the most important searching technique to find the critical point or to find the optimum solution. Thank you very much.